Hello students, welcome to my channel Positron. Today's topic is a torque acting on the dipole kept in a field. Dear students, I am discussing with you all about the electric field, that is electrostatics. Electrostatics are that part of physics in which charge is static. I mean that what a static charge can do, that we study in the electrostatics. In my first video, I have discussed with you charge, its properties, method of charging. In the second video, it was Coulomb's law, undoubtedly vector form of Coulomb's law and electric fields. Then in third video, I discussed with you all the electric field lines, its properties and some other things. Now, today's topic is a torque acting on a dipole. What happens when an electric dipole is kept in an external electric field? Dear student, today's topic is what happens when an electric dipole is kept in an electric field. Now you know that dipole is a what? Dipole, it is a combination of two charges equal in magnitude, opposite in nature, kept at a little distance from each other. So, dipole moment is a one charge multiplied by the distance between them, and the unit of dipole moment is a Coulomb into meter, and dimension is undoubtedly ATL. Now, dear students, what happened? It says the topic is a torque acting on the dipole kept in a field. It means if a dipole is kept in the field, then a torque begin to act. Now, how does torque act? What is the torque? Torque is look here. Here are the two bodies, right? Let's understand the basic concept of torque. Here is a two bodies, and on these, here is a body on which a force is acting like this. This is the F force is acting on this single body, right? The two forces are equal and opposite. So net force, that is F minus F, equals to 0. But what happens if the same force is acting like this? Dear students, in this case, again, on a body, the two forces equal in magnitude and opposite in direction are acting, but here the line of action is parallel to them. In previous case, here in this case, the two forces are acting like this and their line of action was same. The two equal and opposite forces were acting and their line of action was same. In this case, net force is 0. Even in this case, net force is 0. That is F minus F. The two forces are acting on the same body, right? They are equal and opposite. But dear students, here the line of action was same, but here the line of action is parallel to each other. Such two forces will form a couple which will try to rotate. This is clockwise, right? I was discussing this topic because the current topic that we are going to study is based on this very fact that when a dipole is kept in an electric field, a torque begins to act. And what is the value of that torque, we will find. Now, dear students, this is the electric field, right? Direction of electric field. And here is this is plus Q charge, this is minus Q charge, and the distance between the two charges is 2A. This 2A, why do we consider 2A rather to consider A? Simply because if there is a 2A, most of the time we have to take half of the distance. This 2A or A does not matter. This is of order of angstrom. The distance of dipole, distance between the charges in the dipole is order of angstrom, 10 to the power minus 10 meter. We do consider 2A because most of the time you have to consider half of the distance, and that is why it becomes A as A and easily you can solve. Now, dear students, the two charges are plus Q minus Q, and this is 2A, and this dipole is making an angle theta with the electric field. Now, the very basic concept is the, E is equal to, how the E is defined, that is limit Q naught tends to 0, F upon Q naught, right? That is, electric field is a what? Electric field intensity is a what? That is a force experienced by unit positive test charge at a point. Electric field intensity is the force experienced by unit positive test charge. It means the nature of electric field intensity is the force. Actually, that is a force-like quantity, because you define electric field intensity is the force experienced by unit positive test charge at a point. So you can say that F is equal limit Q naught tends to 0 means the test charge is a very little but not 0 at all. So you can say F is equal to Q naught E, right? Now dear students, I mean to say that if a charge Q is kept in an electric field capital E, then there is a force acting Q into E. If a charge Q is placed in an electric field vector E, then the force acting on the charge will be QE. In the case of positive charge, that force will act in the direction of the field. In the case of negative charge, that force will act opposite to the direction of the field. So, on this charge, the force will act in the direction of the field, and in this charge, force will act on opposite of the field. In the case of positive charge, force act in the case of positive charge, force act in the direction of the field, whereas in the case of negative charge, force act opposite to the direction of the field. Now, dear students, we are just drawing it further such that these two lines meet to each other. If this angle is theta, then this is also theta. Now, this is a 2a, right? If you consider sine theta, that is perpendicular upon hypotenuse, so it is a 2a sine theta. Now, dear students, look here. Because of the presence of external field, the charge plus q of dipole experiences a force QE in the direction of the field, and the charge minus q experiences a force QE opposite to the field. These two forces, look here, these two forces are equal, opposite in direction, right? And their line of action is parallel to each other. Their line of action is parallel to each other, right? Yet their vector sum net force will be 0. But if the two forces equal in magnitude, opposite in direction, and their line of action is parallel, then they will form a couple. And this couple will try to rotate the dipole along the clockwise position. So, now look here, it will form a couple. The two forces are equal in magnitude, opposite in direction, right? And their line of action is parallel, so they will form a couple. And now look here, the moment of the force, that is equal to a force multiplied by perpendicular distance between forces. Now, dear student, force is a QE acting on each of the charge, and the perpendicular distance between them is this. Now, this is the line of action. The perpendicular distance between the two line perpendicular distance is that. That is why this is 2a sine theta, and now it becomes q into 2a e sine theta. And dear students, you know q into 2a is what? P, electric dipole moment P. So it is a P e sine theta. And moment of the force is what? That is called torque. Torque is a what? In the case of rotation, in the case of linear motion, you require force. In the case of rotational motion, you require torque, right? Moment of any physical quantity is what? Just multiply that quantity by r, right? Take the cross product of that quantity with the r position vector, that will turn into moment. Like angular momentum is a moment of momentum, r cross p. In similar way, moment is the moment of the force R cross F. Now, dear students, we have got tau is equal to P sine theta. Now, we might write like this. Tau in the vector form, it is tau is equal to P cross E. You know, if vector A cross vector B is equal to AB sine theta n cap, just further in you must have studied in 11th standard, I'm sure, last year. I've made videos also on the cross part. So tau is equal to P cross E sine theta. Tau is equal to P sine theta, or tau is equal to P cross E. Now dear students, look here. If theta equals to 0, this angle is 0. Means dipole becomes like this, or dipole becomes like this. In that case, what is sine 0 is 0, and so tau is equal to 0. It means if a torque is kept along the direction of the field, if a dipole is kept along the direction of the field, there is no torque acting on it. If theta is equal to pi by 2, dear students, means dipole is kept like this, right? In that tau is equal to Pe sine pi by 2. Sine pi by 2 is a 1. That is a tau max. Maximum torque acting, that is Pe. It means when the dipole is kept perpendicular to the applied external field, in that case, the dipole will experience the maximum torque and its value tau max will be P into E. This was the case. Dear students, we are discussing about the torque acting on the dipole when it is kept in a field, external field. I have told you all the basic concept of the torque is what? When a torque acts on a body. If on a body, the two forces are acting such that they are equal in magnitude, opposite in direction, and their line of action is parallel, then they will form a couple. Means the two forces equal in magnitude, opposite in direction, and their line of action is parallel, then they will form a couple which will try to rotate either maybe the clockwise or anti-clockwise. It was a torque acting on the dipole kept in the field. Let's move to the next topic. Dear students, today's the very important topic that we have to study, electric flux. The topic that we have to study especially, and that is the electric flux. Dear students, either be the electric flux, magnetic flux, or gravitational flux. It is, if you are considering the electric flux, it is the dot product of electric field intensity with the area vector. If you are considering magnetic flux, it is the dot product of magnetic field with the area vector. Means any flux is the dot product of area with that physical quantity. Any of the flux, either be the electric flux or magnetic flux, this is the dot product of electric or magnetic field with the area vector. It means electric flux phi E, that is equal to E dot ds, and that is equal to E ds cos theta, where theta is the angle between vector E and vector ds, area vector. Dear students, for example, let field lines are passing in this way. This is the electric field, and this is a plane is kept like this, right? And field lines are crossing perpendicular to it. The direction of area vector will be, in this case, parallel to the ds, parallel to the area. Dear students, the room in which you are sitting and watching my videos, they are the 6 surfaces. Just back to me, front to me, this left to me, right to me, above me and on the ground. In all the cases, if you consider, look here, in all that cases, look here, in all that cases, in this case, area is normally outward. In this case, area is normally outward. In this case, this is that. In this case, it is that. In this case, it is that. And in this case, it is that. It means area vector is always normally outward. If this is the field lines are crossing in this way, now at this surface, electric field line is this, and the area vector is also in the same direction. So, in this condition, vector E is parallel to ds. So, theta equals to 0, phi E is equal to, or d phi E is equal to E ds cos 0 is 1. It might be that your surface is this, means the area vector ds vector is this, and field lines are crossing in this way. This is theta. In this case, phi E is equal to E dot ds, and that is equal to E ds cos theta. Right? Dear students, that all depends on the direction, the angle between the area vector and electric field. Just what I have told you, that the room in which you are sitting and watching my videos, they are the 6 surfaces, right? Just front to me, back to me, left, right, and above to me, there is ceiling, and below the ground, right? The surface on which I am standing. Just consider this box, and outside of the, at this surface, field line, at this surface, field lines will be normally outward. At this surface, field line will be thisward. At this surface, it is field line normally outward. At the bottom surface, field line like this. On this surface, it is this. On this surface, it is this. So, on all the 6 surfaces, or on any of the surface, field line is normally outward at that point. If you consider, this is, right? A charge is kept here. Now, at this point, at any point, field line will be, area vector will be normally to that point, right? Just consider tangent, and this is normal too. If at this point you have to consider the area vector, if this is the tangent and perpendicular to the tangent. In this way, at any, whether it is a regular, irregular, whatever kind of shape body has, it does not matter. The area vector is always normally outward. Dear students, why we are discussing the electric flux? Because we are studying the electrostatics. Electrostatics is a what? If a charge is static, what is the properties that it possesses? What a static charge can do? How many properties does it reflect? That is, we study in the electrostatics. And today's topic is a very important, that is a Gauss law we have to study, and that is why we are studying electric flux. Dear students, we are going to study Gauss law. Gauss law in electrostatics. A very irregular kind of body we have considered, right? Charge Q is kept anywhere in the body. Gauss law is the most practical law, most natural law. It does not consider that wherever the charge is kept. This is kept inside a body, right? The Gauss law is applicable for closed bodies. So, this is a body, irregular kind of body, and this is consisting the charge Q has been kept anywhere within the body. Now, what does Gauss law explains? Dear students, you must have studied the Coulomb's law. Coulomb's law is what? Coulomb's law is if a charge Q is kept, then if a charge Q is placed anywhere, then at a point P smaller distance from it, the field will be D or E is equal to, that is 1 upon 4 pi epsilon naught Q upon R square. In the vector term, you can write E is equal to 1 upon 4 pi epsilon naught Q upon R square, that is R cap. R cap also can be written as vector R upon R. R cap is equal to vector R upon R. So it becomes, dear student, you might write 1 upon 4 pi epsilon naught Q vector R upon R, and this is R square already. So it becomes 1 upon 4 pi epsilon naught Q upon R cube vector R. In this way you can write, or in this way you can write, right? Any way you can write. Now what we have considered here, we are going to study the Gauss law in electrostatics. Like the Coulomb's law, law of gravitation, these are said to be the most natural law in physics. Natural law, I mean to say, there is no mathematical derivation of these laws. If you say that the force is directly proportional to the product of charges and inversely proportional to the square of distance between the two charges, then this is not a mathematical derivation of a law. It is just an experience of a person from thousands of years that have been represented in form of law, right? So dear students, this is it is just a irregular body we have considered because Gauss law is applicable to any kind of body, whatever be the shape, however big or small, no matters. Now dear students, this is a body which is consisting the charge Q, right? Anywhere charge is kept, no matters. Now consider anywhere a small element ds, right? Dear students, this is the direction of area vector, and at this position, let this is the R, and this is the direction of position vector. Now the flux, the flux associated with element ds. With this element, what is the flux associated? Just form like this. Dear students, first we are trying to find out the flux associated with this small element. Then this is what d phi E is equal to E dot ds. Or E is a what? The field due to charge Q at this point. What is the field? That is 1 upon 4 pi epsilon naught Q upon R square R cap dot ds. You might write like this. Just I have written here the Coulomb's law, dear students. The electric field due to charge Q at this area element, which is R distance away, that is 1 upon 4 pi epsilon naught Q upon R square R cap dot ds. Now you might write like this: 1 upon 4 pi epsilon naught Q upon R square R cap dot ds. That is mod of R cap mod of ds cos theta. That is mod of R cap is a 1. Mod of R cap, that is equal to 1 unit vector, and so it is a ds cos theta. Dear student, this is the flux due in this small element. When I was making my first video, when I was discussing first time when I came to the YouTube and discussing with you all, I have told you all, dear students, if you are a student of physics and if you want to have a good knowledge of physics, then you should be at least know, you should be familiar with the three instruments that makes physics easier. First one is you should have a very good knowledge of vector, right? Second one is you should have a good knowledge of graph. At least you should know the nature that what a particular equation represents. And third one is a calculus, I mean integral and differential. My next video will come on, will consider these three topics one by one. That is, first I'll consider the vector analysis, then I will make the videos on graphical analysis, and the third one undoubtedly will be on differential and integral. You should, I'm not saying that you should be master of that, but at least you can solve the problem and you should know up to that extent. Now, dear students, the flux due to charge q in this small element, that is a d phi is equal to 1 upon 4 pi epsilon naught q upon r square ds cos theta. Now, dear student, this is due to a small element. Now, due to whole body, how much flux will be? So, due to flux due to whole body, that is now I'm going to integrate. Dear students, integration is a summation, right? You find the flux associated with that small element. If you will integrate, because this whole body is a composition of such a kind of infinite small elements, and if you integrate it, means you are considering the total flux like so many elements, means total flux due to body. If you just integrate means you like a garland that is made of many flowers in it, right? In similar way, integration, that is a summation, that is a addition kind. This whole body is a made of number of such a kind of small elements, and if you integrate, you find the flux due to one element, and then you integrate means you are going to find out the flux due to whole body, and that is it. Now, dear students, look here, very simple. You can write phi is equals to, now q upon 4 pi epsilon naught is a constant, take out. Now this is ds cos theta upon r square. Dear student, this is said to be that it was our body and there was charge q and it was the element ds, right? This is integral ds cos theta upon r square is the solid angle made by this area element at charge q. ds cos theta, ds is this area element, dear students. ds cos theta upon r square is the solid angle subtended by this small element at charge q. ds cos theta upon r square is what? That is a, this is an irregular body. Here is a charge q kept, and this is a small element ds, right? ds cos theta upon, and this is r. Dear student, ds cos theta upon r square is the solid angle subtended by area element ds at charge q. What is the difference between angle and solid angle? Angle is a 2D. It has the angle equal to arc upon radius, and it has the unit, you know, that radian, and solid angle is a 3D. That is, now consider, now watch the corner of your room from where you are just watching my videos. At that corner, the three surfaces are meeting, and at that corner, the angle is a solid angle. You must have enjoyed the cornetto ice cream. At the bottom of that ice cream, bottom of that cone, the angle is a solid angle, and that is represented in terms of steradian. Now, ds cos theta upon r square is the solid angle sustained by this area element at charge q, but it is an integral ds cos theta upon r square. You might write like this: phi e is equal to q upon 4 pi epsilon naught. This is d omega. D omega is a solid angle sustained by ds at this. Now, dear students, you are considering the integration. Integration means if this small element ds is sustaining, making an angle, solid angle d omega at q, then integral means whole body, what angle, what solid angle, that whole body is going to sustain at charge q. Now, integral means that whole body, what angle is going to sustain, what solid angle is going to sustain at charge q. And dear student, in 3D, you know that whole body makes an angle 4 pi at any point. It does not mean, I have said initially when at the beginning of my video, I have said that charge is kept wherever is immaterial. This is a very general law. So, integral d omega, that is a d omega is a solid angle sustained by element ds at point q. Now, integral d omega is a solid angle sustained by whole body at charge q, and that is 4 pi. So, phi is equal to d strength q upon 4 pi epsilon naught into 4 pi. 4 pi will be cancelled. So, phi is equal to q upon epsilon naught. Or in general, you can write like this: the flux associated phi e is equal to, dear students, you might write phi e is equal to integral e dot ds, and that is equal to q upon epsilon naught. Dear students, phi, electric flux associated with a closed loop. This is a closed loop. This is applicable to the closed loop, not to the open loop. The electric flux associated with a closed loop is the electric flux E dot ds. I have told you that flux is a what? Dot product of area vector with that physical quantity of which you are concerned with the flux. Electric flux, that is a dot product of electric field intensity and area vector. Magnetic flux, that is a dot product of magnetic field intensity and area vector. Now, phi, electric flux associated with a closed loop, that is equal to E dot ds. Electric flux associated with a closed loop is equal to 1 upon epsilon naught times of charge enclosed in that loop. That is, this charge is a total charge, net charge, that might be the combination of positive and negative charges. If a body is consisting many charges, that might be some positive, might be some negative. In that case, you have to consider the algebraic sum like this: q is equal to q1 minus q2 plus q3 minus dot dot dot, right? That is algebraic sum of all the charges. I mean to say that you have to add all the charges with their sign, and then that will be q. So, phi is equal to q upon epsilon naught, means electric flux associated with a closed loop is equal to 1 upon epsilon naught times of charge enclosed in that loop. Dear student, that was the Gauss law we are discussing with you. Now, what is the means of Gauss law? Let's try to understand. Dear student, this law says, look here, integral E dot ds is equal to q upon epsilon naught. Means electric flux associated with a closed loop is equal to 1 upon epsilon naught times of charge enclosed in that loop. This, what are the limitations of this law? That this law is true when charge is kept in a closed loop only. Otherwise, you cannot apply, right? A question is like this. It is asked: Here is a surface and a charge is openly kept at a distance small a above this surface. Here is a surface and a charge q is kept at a height small a or a height small h. What is the flux associated with that surface? You cannot find. Now you have to consider closed loop. Means you have to, if it is h, right? Above its h, now consider a cube of 2h. This is 2h, length, breadth is 2h and height is 2h. If you will consider, dear students, my question is that here is a surface, right? Here is a surface. At height is small h, a charge is kept q, right? And question is that this is openly kept in air, that this is the surface and a charge plus q is kept at height is small h from this surface. Now, question is that you have to find out the flux associated with this surface. How will you find out? Because this is the limitations of Gauss law. Gauss law is applicable, valid only for the closed loop. Now you have to consider a closed loop. How will you consider? Look here. If it is at height h, your charge q is this, right? Now the room in which you are sitting, consider it is a cube of 2h length, 2h breadth and 2h height, and at the center of that a charge q is kept. Dear students, the room in which you are sitting, how will you solve this problem? So, I'm just considering a similar problem. Let a cube which has the length, breadth and height 2h, and at the center of that cube a charge q is kept. Now, dear students, and in this case what? A charge is kept at height small h, right? Now look here. I have considered a cube. Look here. This is interesting. I have considered a cube, right? And each surface is a 2h, length, breadth and height 2h. At the center of that, there is a charge q kept. This cube has the 6 surfaces. Now if you apply the Gauss law, that says phi is E equal to integral E dot ds, and that is equal to q upon epsilon naught. This total flux associated with all the 6 phases, they are the 6 phases. The total flux associated with all the 6 phases is q upon epsilon naught. But in this question, it is asking that the flux associated with the single phase. In this question, there is no difference between the two questions. You can solve this question on this basis. In this case, it is saying that this is a surface and a charge q is kept at height small h from the surface. You have to find out the flux associated with this surface. In order to solve this, we have considered that a cube which is having each edge 2h, length, breadth and height, each edge 2h. At the center of that cube, charge q is kept, right? In that case, the total flux associated with that, applying the Gauss law, phi is equal to integral E dot ds is equal to q upon epsilon naught. Means total flux associated with all the 6 phases is q upon epsilon naught. But in this case, the question is, the difference between these two is what? In this case, the total flux associated with the q, and that is q upon epsilon naught. And in this case, the flux associated with the single phase, and that will be 1 upon 6 of q upon epsilon naught. Because this q upon epsilon naught is what? That is the flux associated with all the 6 phases, and in this case, this is the flux associated with the single phase it is asked. That is why the answer will be 1 upon 6 q upon epsilon naught. Dear students, let's move further. Further is applications of Gauss law. How the Gauss law what are the applications of Gauss law? How you can apply, right? Case first, field due to point charge, right? Field due to point charge. As you usually find using Coulomb's law, here is a plus q charge. A point P is a smaller distance away. Now, you applying the Gauss law, you have to find out the field at point P. You know, Gauss law you can apply only on the closed surface. This is open. So what I am doing, we are considering a sphere of radii on which a point P exists. Because Gauss law can be applied only on the closed loop, so in order to apply the Gauss law, I have considered a sphere of surface is smaller on which charge point P exists. Dear students, at this point look here, this is a area vector, direction of area vector and electric field. In order to find out the direction of electric field at any point, just imagine a positive test charge. If you will imagine positive test charge, that will be repelled in the same direction. It means in this case, at P, vector E is parallel to vector ds. So E dot ds is equal to E ds cos theta. Theta equals to 0. So it is a E ds cos 0 equal to 1. The flux associated with this small loop, integral E dot ds, right? The flux associated with this small loop is E dot ds d phi E. Flux associated with this small loop is a E dot ds. Total flux associated with our total sphere, that is phi E, we have integrated, that is E dot ds. Now dear students, that is what? E ds cos 0 is 1. Now dear students, look here, at each point on the surface of the sphere is at equal distance away from charge q, at a distance of radii smaller. That is why E is a constant. In the case of constant, you can take out from the integration. So it becomes, now phi is equal, that was equal to q upon epsilon naught, that was equal to q upon epsilon naught. So E integral ds is equal to q upon epsilon naught, and E integral ds is that much area. Integral ds means area, total surface area of the sphere, and that turns out to be 4 pi r square, that is q upon epsilon naught, or E is equal to 1 upon 4 pi epsilon naught q upon r square. This is what result you have got in the Coulomb's law, that if a charge q, if a point P is r distance away from point charge q, then the field at that point E is equal to 1 upon 4 pi epsilon naught q upon r square. That the challenge here was using the Gauss law. It was a charge q, a point P is here, which is smaller distance away. We have to apply the Gauss law. That is why, because Gauss law is applicable only in the case of closed surface, that is why we have assumed a sphere of radii small r, and this sphere is called to be the Gaussian surface. Dear students, this is a small element ds. Now at this point, imagine a positive test charge. This test charge will be repelled like this. This is the direction vector and area vector is normally outward. So E and ds both are in the same direction. So E dot ds is equal to E ds cos 0. Cos 0 is 1, that is E ds. Now flux associated with this much, that is d phi is equal to E dot ds. So with total, that is phi is equal to, if you will integrate d phi, if you will integrate, that will result into phi. In similar way, d phi is the flux associated with this element and phi is the total flux associated with this spherical Gaussian surface. Now this is phi is equal to integral E dot ds, and that is equal to, if you are applying on the closed surface, then total charge inside this surface, wherever, either here, wherever is kept immaterial, this is the sum, algebraic sum of total charge enclosed in that. That is a q upon epsilon naught. Now dear students, all the points on this surface are equal distance away from the charge. It means electric field, the magnitude of electric field at every point of the sphere is a constant. So the constants can be taken easily out of the integration. So E I have taken here. E integral ds is equal to q upon epsilon naught. Dear student, ds is the area of the element. Integral ds is the area of total sphere, that works out to be 4 pi r square. So E is equal to 1 upon 4 pi epsilon naught q upon E equals to 1 upon 4 pi epsilon naught q upon r square. That result already we have got the field due to point charge using the Coulomb's law, and this is using the Gauss law. Actually both are counterpart to each other. Now let's move further. Case 2, field due to sphere. Due to spherical shell. First we will do spherical shell. Right? Dear students, here we have to discuss the three things. Dear students, here we have to discuss the three things. One is a hollow sphere, then solid sphere and spherical shell. Solid sphere means in which material is filled from center to the surface. At every point there is a solid, it is consisting of material. In hollow sphere, what is hollow sphere is that much in which there is, if a smaller ball is taken out from the solid sphere, that turns out to be the hollow sphere. Hollow sphere is what? From the solid sphere, a smaller solid sphere is just taken out. Then it becomes internal and external radial, right? And a spherical shell is what? A spherical shell is also a hollow sphere, but thickness of its material is a very little, negligible, right? So this is also a hollow sphere, but the thickness of the material is very little. It means it does not have the concept of internal and external radial. In this case, we consider only the radii of the spherical shell. Now, dear students, field due to spherical shell. Case first, A. When point is outside of shell. This is a spherical shell. It has the radii r. A point P is existing at a small x distance away from the center, where we have to find out the field, right? A point P is a small x distance away from the center, where we have to find out the field. Dear students, look here. In order to find out the field at, let it is a smaller distance away, this is the center, and point P is a smaller distance away from the center, we have to find out the field. Dear students, this is a spherical shell, means inside there is no material at all. It means charge is just distributed at the surface of the shell, because inside it is empty, right? So charge is distributed on the surface of the spherical shell. Now, dear students, you can see that field will just begin from the shell and will go out of the sphere like this. And if these fields are produced back, they will meet actually at the center. When these fields are produced back, they will meet actually at the center. It means it appears that these field lines are coming from it appears that these field lines are coming from the center. Actually, when point is out of the surface, out of the spherical shell, then it appears that the field lines are coming out from the center. Now, in order to apply the Gauss law, you have to consider Gaussian surface, and that is why we have considered a Gaussian surface, a sphere of radius small r on which the point P exists, where we have to find out the field. Dear student, this is a spherical shell on which charge Q is distributed. The radius of the spherical shell is capital R. A point P is a small r distance away from the center C, where we have to find out the field. In order to find out the field at point P, what we have done, what we have supposed, I have assumed that if a spherical Gaussian surface or a sphere, a Gaussian surface or Gaussian surface is a sphere of radius small r on which the point P exists, where we have to find out the field. Now, so you know the flux associated phi is equal to integral E dot ds, and that is equal to total charge. This whole charge is inside this Gaussian surface. This is our Gaussian surface. Q upon epsilon naught. Now again, at this very point, E and ds again will be in same direction as in previous topic we have discussed that. E ds cos 0, that is equal to Q upon epsilon naught. Cos 0 is 1. Again, at each and every point are equal distance away from the center. So E is a constant you can take out, that is Q upon epsilon naught r. E ds is a what? 4 pi r square, that is equal to Q upon epsilon naught r. E is equal to 1 upon 4 pi epsilon naught Q upon r square. This is the. Now dear student, this is Q for the field due to point charge at a distance small r away, right? This is the field due to point charge. It means if the point is out of the shell, if the point is out of the spherical shell, then the whole charge you can assume that it is kept at the center and behave like a point charge, because similarly to a point charge you have got that result. Now dear student, this was the case when the point was outside of the shell. The case B, or second case of that, when point is inside the shell. This is the shell, has the radius r, charge Q is distributed on the surface of the shell, because inside the shell it's empty, right? This is plus Q distributed on the surface of the shell, and inside the shell is empty. Now you have to find out, let a point P is small r away from the center, and that is inside the shell. Now dear students, now again applying the Gauss law, phi equal to integral E dot ds, and that is equal to Q upon epsilon naught. Now inside the shell, in fact, the charge is residing at the surface of the shell. Inside the shell, there is no charge, and so inside the shell, Q equals to 0. So integral E dot ds, that turns out to be 0, so E equals to 0. So inside the spherical shell there will be no field. This is used as this very property of spherical shell is also called electrostatic shielding. This is the case when you are just going on in downtown or going for hangout or on a trip from your car and there is a thundering and lightning in the sky. Then how you can save yourself? Just close the car, right? And put off the engine and switch off the engine and just sit there. Nothing is going to happen because inside the charge will, if the electric lightning comes to your car, then charge will be distributed on the surface. If the windows are closed, then electric field cannot penetrate inside the car, so you will not be hurted, and this is called to be the electrostatic shielding. Electrostatic shielding is what? This is, you are sitting inside the car, means you are sitting inside the spherical shell. When the electric lining falls on the surface of your car, on the roof of your car, charge will be distributed on the surface of the car, but the windows are closed, so field, because inside there is no charge, so according to Gauss law, field inside the cell will be 0, inside the spherical shell field will be 0. In the similar way, inside the car, despite when the electric lightning falls on the roof of your car, charge will be distributed, but the electric field cannot penetrate inside the car, and this is called to be the electrostatic shielding. Dear students, one thing is very important, that significance of Gauss law. This says E dot ds is equal to q upon epsilon naught. It means the physical significance of Gauss law, wherever there is a field, there is a charge, there is a field. Charge is the only source of electric field. According to this Gauss law in electrostatics, integral E dot ds is equal to q upon epsilon naught. What does it mean to it? That wherever there is a charge, there is a electric field. Means charge is the only source, charge is the only resource of electric field. Means I do not know. This law do not reflect, this law do not tell us that whether the charge is static or moving or accelerated motion. Nothing it talks about. It talks about that if there is a charge, there is a field. Right? Means a static charge or dynamic charge is immaterial. According to this, like charge exists, there will be field, and charge is the only resource of the electric field. Today I have discussed with you all that the torque experienced by electric dipole kept in a field, what is the electric flux, then I came to know Gauss law, one application of the Gauss law. A lot of applications are still left, I know well that. Because video is going to be long enough, if today I am going today if I will discuss with you. So dear students, in next video undoubtedly the rest of applications of Gauss law I will discuss with you, and a lot of interesting things we will talk about. So if you think that my videos are beneficial to your studies, I am trying my best to let you understand, to make the physics familiar and easy. Teaching is just hard, dear students. So I'm trying to make the physics very simple for you all. If you think that my videos are beneficial to you, then it's again and again what every time I used to say that is from deep and sincere my heart, I do request, please and please like, share, subscribe, and do comment, so that I can, this every of your comment will motivate me. Okay, meet you in next video. Bye bye.